Hi everyone, welcome to the 16th episode of Math and Beyond Anomalies podcast. Today we are going to talk with, I hope I get this right, Nina Hernitschek. She's a researcher in astronomy, and today we are going to talk about we have quite some topics. One of these is the history and evolution of the Milky Way, of galaxies in general, and then we're going to on to variable stars, and we're also talking about machine learning methods that can be used in astronomy. So I'm going to send the invite, and I will see you short. Hi, Nina.
Hi, thank you for inviting me.
Hi, thank you for accepting. It's a great pleasure to talk with you. How are you?
I'm good, and I'm currently here in Antofagasta, Chile, and it's technically winter here in the South Hemisphere, but here it stays warm all year long.
Okay.
So, yeah, I just moved 2.5 months ago to Chile to start my new position as an assistant professor in astronomy.
Okay.
And that's, of course, an exciting thing, and I really like it here. And like many astronomers, I've lived on more than one continent. So years ago, I did my PhD in Germany at the Max Planck Institute for Astronomy, and after that I went to the US for a postdoc position at Caltech, and then at Vanderbilt University. I was working there on survey design, so astronomical survey design, machine learning methods for discovery and characterization of variable stars. And I'm especially interested in those stars as they serve as tracers for the dynamical history of our Milky Way.
Okay, thank you. You saved me one question. Tell us a bit about your academic history. So that's great. We already covered this. I want to ask you also. Your last. I was about to introduce your last position at, I just said, at the Vanderbilt University as a postdoctoral fellow, but you already mentioned it. I already gave a small introduction about the topic of discussion of today, and so I think we can jump into the topic of discussion. And as you said, you dealt with the dynamical history of the Milky Way. So I would like to start from here, and I would like to ask you if you can bring us along the history of the Milky Way. How does it form? And let's say, what are the early stage, what is the phases of the early stage formation of a galaxy?
Yeah, so regarding the formation of galaxies, there are in fact multiple series which differ in their details, but overall, nowadays we have pretty much understood how galaxy formation works. So for this, I will look back at how our universe looked some 13 billion years ago. That's about 1 billion years after the Big Bang. And that's when the first galaxies formed. So our own galaxy, Milky Way, also formed at that time. And it's approximately 13.6 billion years old now. In contrast, the youngest galaxies we know have formed only about 500 million years ago. So regarding the initial stages of galaxy evolution, or let's say better, how galaxies have formed, so on scales which are much larger than galaxies, gravity has pulled together matter to form a web-like structure of filaments surrounding some nearly empty voids in between. Galaxies are believed to form along those filaments and accumulate in clusters, where the filaments are intersecting, so at the nodes in the web. Our own galaxy is belonging to the local group, of which the two largest members are the Milky Way itself and Andromeda galaxy, both of them being spiral galaxies of about 10 to the 12 solar masses. So when we look back in time, we have to go to deeper redshifts, to more distant objects. And indeed, there we can see indicators for galaxy formation. So when a galaxy-sized cloud of matter is collapsing, then stars form within it. And the stars and the interstellar matter in a galaxy finally settle into orbits around a common center of gravity. And when those proto-galaxies are contracting, they're rotating faster and faster. Just, you can imagine it like an ice skater pulling in their limbs when dancing. It's exactly that process. In that way, the rotation is counteracting gravity along a plane and allowing collisions within the gas to produce the disk of a spiral galaxy, just like we observed. Galaxies, furthermore, can collide and merge to then form more massive galaxies. So when two about equally sized galaxies are on collision and finally collide, the spiral structure in them is lost because of the gravitational interaction. So the stars themselves are not colliding, but just this conglomerate of stars is colliding in that their orbits, and their spiral structure of the disk is lost. And then an elliptical galaxy forms. So that's happening to probably all large galaxies, more or less, that they grow by consuming smaller ones, which did also our Milky Way, but it has only consumed small galaxies, so the spiral structure wasn't lost. There's one more thing I want to highlight here because it's really interesting, is that within the local group, the Milky Way and the Andromeda galaxy are gravitationally bound and are currently approaching each other at a pretty high speed. And simulations are showing that the Milky Way and the Andromeda are on a collision course indeed, and are expected to collide in less than 5 billion years. And that remnant could be a giant elliptical galaxy.
Okay, can I ask you, before proceeding through the history of the Milky Way, what, let's say, theoretically happens when Andromeda and the Milky Way galaxy collide? Do they, let's say, what happens? Because we know that at the center of our galaxy, there is a black hole. So what are the processes that will be involved when these two galaxies will collide?
So indeed, there is a big supermassive black hole inside each of those galaxies, but there are also smaller black holes surrounding that large one. So nowadays we believe when they are colliding, so the galaxies are colliding, then not much is happening to the stars themselves. They will change their orbits. But what will happen is that the black holes will merge, and this can also trigger star formation processes later on. Okay. So the overall look of that galaxy will then change dramatically. Okay, so it will be overall a very disruptive process for the, let's say, layout, the current layout of both galaxies. Yes, so it will disrupt those galaxies to form a new one. I would not really call it a violent event, because generally these are events in which more objects are destroyed or something else is happening. It will be, I would say, it will be more slow and silent change in how this galaxy looks like. Okay, so what about instead the Galactic Halo, which is one of the, say, big main component of a galaxy? How do we, let's say, how does a galactic halo form? How did our galactic halo from the Milky Way form? What is it composed of? Yeah, so indeed, the galactic halo is a very, very big component. Often people think of a galaxy as a flat spiral. That's how they look like in most photographs. But I think it's better from an astronomical point of view to think of a spiral galaxy as a sphere with a low stellar density, so only a few stars per length unit, and an embedded disk with spiral arms containing the majority of stars. And this surrounding sphere, that's the halo. So that's about 1% of the stellar content of a Milky Way-like galaxy, and those stars are old. So the halo itself, it has multiple distinctive components, which are the stellar halo, then the galactic corona, consisting of hot gas, so plasma, and then there is the dark matter halo. The distinction between the halo and the disk, the main body of a galaxy, is the clearest in spiral galaxies, where we have this spherical shape of the halo that's contrasting a lot with the flat disk. However, in an elliptical galaxy, we also have a halo, but there is no sharp transition between the other components of a galaxy and the halo. So the stellar halo is a nearly spherical population of field stars, so background stars, as we call them, and globular clusters. And it's surrounding most disk galaxies as well as some of the elliptical ones. The Milky Way stellar halo contains globular clusters. They contain Lyrae stars, so those are periodic variable stars, more on that later on, and they're containing subdwarfs. Stars in our stellar halo tend to be old, so most are older than about 12 billion years, and they are metal poor. So the halo stars of the Milky Way also have an observed radial velocity dispersion of about 200 kilometers per second and a low average velocity of rotation of about 50 kilometers per second. So that's very different to disk stars. The star formation in a stellar halo of the Milky Way has ended long ago. So what we then have is the galactic corona. That's a distribution of gas extending far away from the center of the galaxy, and we can detect it by distinct emission spectra showing the presence of H1 gas, that's a 21 centimeter microwave line, and other features which are detectable by the X-ray spectroscopy.
Okay, you mentioned before globular clusters. Can you expand a bit on what are globular clusters and, let's say, where do they enter the picture in halo formation?
Yeah, so globular clusters are technically some spheroid star clusters which are bound together by gravity, and they have a higher stellar concentration towards their centers. They can be observed pretty easily, and they contain anywhere from 10 to thousands to many millions of stars. Globular clusters can be found in nearly all galaxies. In spiral galaxies like our Milky Way, they are mostly found in the galactic halo. So our Milky Way has more than 150 known globular clusters, and we guess there may be many more, especially smaller ones, that we were not able to detect yet. Their origin. So the origin of globular clusters and their role in galaxy evolution are still somewhat unclear. Some are among the oldest objects in the galaxies and even in the universe, and so constraining estimates of the galaxy's age. Star clusters were formerly thought to consist of stars that have all formed at the same time from one star-forming nebula, which would lead to a roughly uniform age and metallicity. But modern observations show that nearly all globular clusters contain multiple stellar populations. So the globular clusters in the Large Magellanic Cloud exhibit a bimodal population, for example. So we have two populations. Some clusters might have multiple episodes of star formation, and some maybe remnants of smaller galaxies which were captured by larger galaxies.
Okay, Can I ask you if the globular classes are fertile, let's say, places for life?
Your
Meaning
question
around them, of course, not on the stars themselves.
Okay, so your question is whether it is likely that life forms we see in a globular cluster.
Yes, around globular clusters. Yeah.
Okay, so that's a good question. It's not exactly the focus of my research, but from my point of view, I see no special reasons why we would rather have planets with some life forms around stars in globular clusters. I would intuitively more search for them within the disk, but it can never rule out. So but it's nothing special regarding the formation of life forms or organic molecules at all.
Okay. Okay. What is that about? Let's say satellites. What are they? What are satellites? What do we mean by them? And what's their role in halo formation?
Yeah. So with satellites here we mean satellite galaxies. So those are smaller galaxies that are gravitationally bound to a large galaxy. One example for this is also dwarf galaxy Sagittarius, which is trapped in an orbit around our galaxy. And those smaller galaxies were pulled in by gravitational forces and are then stretched out in long shapes, producing so-called tidal streams that we can observe very well. And with them, we can also probe, for example, the gravitational potential of our Milky Way, or we can also do other things, like, for example, doing computer simulations, where we are going back in time and trying to find out what was the small satellite galaxy in the beginning that was producing that tidal stream. So this is in combination with halos, something that leads to tidal streams that can be observed.
Okay. What about instead, you mentioned before dark matter. Where do we find the dark matter in the galactic halo? And say, does it play a role? Again, does dark matter play a role in halo formation?
So dark matter is known to be present in the halo. We can measure this indirectly by rotation curves. So we're tracing the rotation of stars throughout the disk and the halo. And this effect was first recognized by the astronomer Vera Rubin in the 1970s. She has detected a discrepancy between the predicted and observed angular motion of galaxies when she was studying galactic rotation curves. So what she found was that all those rotation curves looked like there was a large amount of matter in addition to what we can observe as stars. Then people started to think about, what is that? Are there some gas clouds we cannot see? It wouldn't match up. And then this term dark matter was created, which is describing matter that is interacting gravitationally, but it is not interacting electromagnetically. So we cannot see it, not only because it is dark in a visual sense, but it's not interacting electromagnetically. So looking at it with a telescope or with an infrared satellite will not produce any results, but we can see how it interacts gravitationally by distorting the movement of other objects in a galaxy.
Okay. Yeah, sure. That matter still plays. I mean, it is sort of one of the hot topics today in astrophysics or cosmology, let's say. But yeah, what is that about disk formation? What is the galactic disk? How did our galactic disk form?
That's, of course, a very interesting question, as the disk is just standing out so much from a spiral galaxy. And that's exactly what we see when we see a typical image of a galaxy. That's the disk. And those galactic disks are very thin and basically circular distributions of stars, some gas, some dust. And this material moves on nearly circular orbits around a common center. The stellar population of galactic disks tend to exhibit very little random motion, with most of its stars undergoing nearly circular orbits. As there is very little vertical motion, disks can be fairly thin. So the Milky Way disk, for example, is approximately 100 light years, say, compared to a diameter of 120,000 light years. So when we look back at how galaxies were born, so most of the stellar component of galaxy we see to be in the flat disk instead of in the sphere. And why did this happen? Galaxies are flat because of their rotation. Remember that pretty much every object in the universe is in a constant movement, and this includes also black holes, which are just like stars rotating around their own axis and also have a trajectory. Sometimes they're orbiting other black holes, like after a merger event, or galaxies, or they might be simply wandering aimlessly across the universe. And matter clumping together creates a galaxy core with a supermassive black hole at the center. The matter in a cloud will move chaotically in every direction just at a star, but with time, it will start to rotate in the same direction as the black hole that's contained.
Due to gravity, of course.
It will rotate in the same direction, yes.
Okay. Instead, I want to ask you, does gravity and magnetic field play a role within for the galactic disk and for, let's say, within the galactic disk formation phase?
Yeah, so gravity plays clearly the largest role, and then just when you imagine how heavy, how massive those black holes are, and then when you compare this to the role of magnetic fields, then you see that really it's gravity, but also magnetic fields contribute to the structure and the evolution of the interstellar medium and the host galaxy. So they affect, for example, the creation of disk by dark matter halos, and we also know that they affect the outflows and inflows in galaxy that have already formed. So by that, they can also trigger or stop star formation. So that's the role of magnetic fields, but gravity is what it's attracting everything and holding it together.
Okay. Can I ask you instead very quickly regarding gravity? This is, let's say, a thought that I sometimes try to wrap my head around. If let's say Newton told us that gravity is a force, right? One of the four fundamental forces. But Einstein later told us that gravity was actually an effect of the space-time curvature. Can I ask you, why do you think now, maybe it is very trivial to ask, but I just cannot understand, why now people still call gravity a force? Why is it still called to be a force, one of the four fundamental forces? And people want to treat it as such.
Yeah, so it is a force because it acts on matter, but the view of how it's actually working and how we can explain its specific properties, that's a matter of, for example, the general relativity. So this is explaining why it has the observed properties. but treating it as a force will just describe that it is interacting with matter and that it has an influence on matter.
Okay. So going on progressing through the evolution of our Milky Way of a galaxy, I want to ask you instead about the spiral arms, which is term which I would find, let's say, quite frequently when getting ready for this conversation. What are the spiral arms of a galaxy, and what are the bars, which is another term I found? Let's say, what are they, and how did they evolve this way?
Yeah, it's indeed associated with a long-standing problem, because we know about the spiral arms in galaxies and in our own galaxy, but then immediately the question comes up: how did they form? Why we can still see them? So first one might think, okay, the spiral arms, it's something that is wound up. But then in 1925, the astronomer Bertil Lindblad realized that the idea of stars being arranged permanently in a spiral shape is just not working. And since the angular speed of rotation of the galactic disk is varying with distance from the center of a galaxy, radial, or like a spoke in a wheel, would quickly become curved as the galaxy rotates. First, this would look fine and could explain spiral arm formation, but then this spiral arm would, after just a few galactic rotations, become increasingly curved, and it would wind around the galaxy even side with a lot more rotations, and this is called a winning problem. This would lead to galaxy shapes that we are clearly not observing. So why they look like they do? So that spiral arms still exist is indicating that they are not rigid and they are not permanent structures. If they were, they would have been wound tighter and tighter through the differential rotation of the galaxy and would have disappeared by now, just when we look at their ages. But Lindblad suggested density waves instead. That's a model that was elaborated in the 1960s as a so-called quasi-stationary density wave model. And this picture requires a collective mode in which stars in the disk behave like a self-gravitating but collisionless fluid. Think of fluid dynamics, which is clumping in a specially periodic wave. And this wave of density differences is then feeding back into the gravitational potential, where it's then serving as the means for supporting the disk wave structure. So we have density waves instead of some shapes that are fixed in space. And exactly that's now the leading model that spiral arms arise from the passage of a density wave through a galaxy. Alternatively, or in addition, there might be very short-lived structures that can be created temporarily as some localized star formation areas, but this is only in addition. And together, both mechanisms, density waves, and some smaller structures fixed in space might explain different kinds of spiral structures that we're actually observing. So then one other component you mentioned, that's the bar. Some central bar-shaped structures are found in about 2/3 of all spiral galaxies and also in our Milky Way. And they are thought to form when stellar orbits in a spiral galaxy become unstable and deviate from a circular path. So the creation of the bar is generally thought to be the result of a density wave again, but radiating from the center of a galaxy. And this density wave is then reshaping the orbits of the inner stars. So you can imagine the orbits are then no longer really circular, and this effect builds up over time to stars orbiting further out and is then creating this self-perpetuating force structure.
Okay, you mentioned before, I think I understood correctly, the winning problem.
Yes.
Is that right? Okay, can you briefly describe what is it about the winning problem?
So it's basically describing which structures in a galactic disk we would have to expect to see if we would have some connected fixed spiral disks within a rotating galaxy. And then we would have some differential rotation, which is then causing the structure to become more and more kind of wound up. And then what we have is not what we see right now. And there must be something that is preventing spiral arms from this happening. And the solution is clearly that spiral arms are not like that, but are temporarily shaped by density waves.
Okay. Then I would like to ask you, we already talked about, I want to cover the, let's say the point of, let's say galactic interaction, which we already, let's say, talked about for the future, so the collision of Andromeda and the Milky Way, but I would like to ask you about the past. Do we know of any past galactic interaction? Who did we touch in our in the formation of the Milky Way, in the history of the Milky Way?
Yeah, so we nowadays know a lot about that. For example, thanks to our surveys we can take with Gaia, with Pan-STARRS, and so on. And what we know nowadays is that there were a lot of mergers happening within our Milky Way. We can also trace back stars based on their metallicity. And we also now know that the streams, the stellar streams we can observe in the halo of our Milky Way, that they are the result of merger events.
Okay. And let's say, are there any major galactic interaction that we know of that we were able to map?
So major interactions can be, but we're not absolutely sure about that, heavily to the distortion of the plane of the Milky Way itself. So we know that it's not really flat, but it's warped a bit. This was also just discovered rather recently. And we believe this is also a result of not really a merger, but a passing by a galaxy that has led to this distortion.
Okay. Okay. And what is that about stellar population? What does, let's say, the stellar population of a galaxy can tell us about the evolutionary processes that have taken place within the galaxy, and what also about timescales that we can infer from different stellar populations?
Yeah, so from stellar populations, what we are typically doing is that we assume that they formed together, and we are, for example, looking for stars with a very similar assumed formation history, which can be found, for example, by their metallicity and age. And we'll look where we can find them throughout our galaxy. And so with that and with computer models, we try to trace back where they have actually formed. And in some cases, we can also find stars which look like they have formed not within our Milky Way. So that's something that can only be done with very large data sets to find out those few stars in billions of stars that show the properties for which we are looking like. And this can be done, for example, with data from Gaia, that we look for stars which basically have a twin, and we try with computer models if we can actually trace back their orbits to a common location of formation.
Okay, can I ask you, how do you how do we understand whether star? Yeah, how do we detect whether a star has been formed outside the Milky Way or not? Because it is quite, let's say, it is quite common to know that there are how much 100 billion stars or even more in the Milky Way. Only how do you know if one has formed within or outside?
Yes, that's indeed not such an easy process. So what we rely on are spectra, which tell us something about the chemical composition of a star. And then we can measure orbits. And from those two and computer models, we can see that, for example, a star is, let's say, basically behaving differently than typical stars within our Milky Way. So it's just in a different location of parameter space. It's not matching to the other stars. And then we can, for example, run computer models. We can go back virtually a bit in time where the star has been before. Does this make sense that it belongs to the Milky Way? And so we can trace this back over time and can get an idea whether this star has likely formed within the Milky Way or has not.
Okay. What is that about? You mentioned before, but I think now it's quite common to know that at the center, let's say not scary anymore, to know that at the center of our galaxy there is a black hole. And firstly, I would like to ask you: is there a black hole at the center of every galaxy? Or do we have galaxies where we do not find black holes at the center?
And so at the center of each galaxy, as far as we know, nowadays there is a black hole, and typically there is not only one black hole, but multiple, and that's also true for our Milky Way.
Okay, and second of all, then I would like to ask you, how did our black hole forms? Because I find it, I would say, if I think about evolutionary process of Milky Way or a galaxy in general, I would depict it, of course, with the center of black hole, or the bigger structure revolving around it. But a black hole is just a type of end of a star. It is a star that has collapsed on itself. So how did at least our form, and how did it, let's say, influence the evolution of our galaxy? Because well, I'd say, let's say, my intuition, which may be wrong, might say, okay, well, if before, let's say, time X, there was not a black hole in the Milky Way. After time X, at time X, we do experience a star collapsing into a black hole. Well, how does the progress, the evolution of the Milky Way or a galaxy changes after time X?
Yeah, so indeed, most black holes form from the remnants of a large star that's dying in a supernova explosion. And smaller stars are becoming dense neutron stars, but larger stars are forming a black hole at the end. And indeed, when there were first indications of a black hole in the center of our Milky Way, then researchers thought about how big was that star that formed that big black hole. But in fact, it was not a star. It's a qualitatively different type of black hole in our Milky Way, and it can be caused, or it can be produced by the gravitational collapse of gas in the central regions of a galaxy. So this so-called supermassive black hole likely was there all the time during the lifetime of our galaxies, and it has millions or even billions solar masses. That's a supermassive black hole inside of a galaxy. And it's even thought if maybe galaxies have started around by then smaller black holes which have increased.
Okay. What do you think when you think about black holes as main major driver of galactic evolution? Because I do consider them as being quite let's say the main character upon which everything revolves around. They are pretty let's say characteristic and pretty strange objects, very simple but at the same time very, very weird. I would like to ask you, what do you think about these objects? Are they, let's say, proxy for new and undeveloped theories of some new physics that we have not discovered so far? Or are they just, let's say, a byproduct of when something within our universe goes wrong and then, okay, you have a black hole, whatever?
Yeah, so I don't think of them as proxies, but I think of them really as massive objects from which light cannot escape. But I know there are, in general, many weird things about black holes and also many misconceptions. So one of the most common misconceptions is that black holes would suck in just everything, and some people, but not researchers, even fear that the central black hole might suck in the galaxy, but that's clearly not happening. So such an object at the center of our galaxy is influencing the movement of stars and dust near it, but it's not sucking in everything. It's especially the case that they can accelerate matter in the form of jets and outflows of gas. And there are sometimes those outflows are sometimes called winds that spread atoms throughout the galaxy and can either boost or throttle down star formation, also depending on other factors. And this means supermassive black holes play a very, very important role in the life of galaxies and even far beyond what is just the gravitational pull of a black hole.
Okay. Well, I would like to ask you now about we talked about, let's say, the dynamical history of the Milky Way. We considered quite some stages, quite some phases of galactic formation. But I would like to ask you if you could explain us where does machine learning enters the picture in this let's say in this understanding, in the comprehension of these processes. How machine learning can help us better understand these processes.
Yeah, so I think here I start with explaining first what machine learning itself is, because I believe that there are about as many misconceptions around machine learning than about black holes. And machine learning are basically algorithms that enables computers to learn without being explicitly programmed. So this is technically allowing us to uncover some hidden correlation patterns through some iterative processes and is usually assisted by examples of certain data. In more technical terms, this allows us to find some transformations from a parameter space of measurements into a parameter space of, in our case, astronomical objects. So in this way, we can then better understand our data and especially work with massive data sets in which it's hard to find information hidden, just like I mentioned a bit earlier regarding finding strange stars within Gaia data. We have to find a way on how to work with these massive data sets. And basically, there are many kinds of machine learning methods, such as clustering, classification which generally fall into the regime of either supervised or unsupervised classification methods. Supervised means that this algorithm is drawing information from examples. So that's a training set. So the core concept of supervised learning is making use of a training set. A training set consists both examples of objects, of data inside and outside the category we are looking for. And they have the same data quality as the data to which we apply our algorithm later on after the training. So basically you can see it as a data set telling this is an example for what we are looking for. And then it complements a set of that's an example for what we're not looking for. And based on that, a supervised machine learning application can draw conclusions in a shape of building up binary trees.
Okay. And let's say, what about, let's say, where do they enter the picture of, for a better understanding of galactic evolution and the properties of a galaxy? How do we exploit machine learning with this regard?
So for the application of machine learning, we have basically two different goals: filtering information,
Bless you. Okay, so also I wanted to ask you, sorry, because from the type of let's say sort of activities, let's put it this way, that I was looking into it with regards to machine learning application. I also found about, as you said, galaxy classification, but also redshift estimation.
Yes.
So, and also, for example, stellar population analysis. So maybe later you want to touch into these kind of processes.
Yes, exactly. So one thing you might know, for example, Galaxy Zoo, that's citizen science project that enables users to classify galaxies. And that project was started because at that time, machine learning was less powerful in classifying galaxies. But nowadays, many machine learning techniques can absolutely keep up. And that's an application of filtering information. And I've also mentioned the usage of machine learning to better understand information. And for that, a typical application is absolutely what you mentioned. So photometric redshifts. Redshifts are typically estimated by taking spectra. So we measure the shift of spectral lines from their at rest, so lab position. And what's a limitation of this is that scanning the sky with spectroscopy is way harder than to do it with photometry. What we then do is building photometric redshifts as an estimate for the velocity of an object, such as a galaxy or a quasar, but we make this without measuring its spectrum. And this technique is using photometry, so brightness of object viewed through various standard filters, to finally determine the redshift. It was developed first in the 1960s, at that time, of course, without any machine learning. And it wasn't widely used because then we had bigger surveys which were capable of taking spectra. But nowadays, our photometric surveys are covering so much of the sky and so deep that we just cannot keep up with spectroscopy. And so we have found ways on how to make use of this old technique again, but now assisted with machine learning. And what we're doing is we're building a training set containing photometric and spectroscopic observations of galaxy. And this approach was then chosen for the SDSS data release 12 because of the overall higher precision we can get with machine learning.
Okay. Yeah. So regarding machine learning, we may touch a little later on. And now I would like to move on to variable star, which is one of your topic of research, of expertise. And I would like to ask you, what is a variable star, and why do we say that it is variable?
Yeah, so variable stars are indeed a very interesting topic, and there are generally two types of variable stars. One of them are intrinsic variables, so stars who have an energy output that's actually varying. And there are extrinsic variables. So there are stars that only appear to vary because of some geometric effects, like eclipses in binary systems. For a long time, variable stars were discovered only sporadically. So among the first variable stars discovered were periodic variable stars, which stand out pretty much as stars that are sometimes visible, then disappear, and then reappear again. Supernovae, at contrast, were known much earlier, but variable stars which show some repeating cycle of variability were not known until the 16th century. So in the 16th century, they were noticed as kind of a curiosity, but then a bit later, they were discovered more and more. So by 1850 about, we had 18 variable stars known. But only about 60 years later, the American Association of Variable Star Observers was founded. So they were discovered and people were very interested in them because, for example, one of the big questions by that time was what is causing that variability and why it is so periodic. So one theory that was proposed is that variability might be caused by eclipses of the star by a planetary companion, so that those were exoplanets. They were not, and we know today that it would have been not feasible to discover any exoplanet with the telescopes at that time. And we know nowadays that variable stars, like for example Algol, or a multiple star system, especially Algol is a 3-star system consisting of the stars Beta Persei B and C, and they regularly pass in front of each other and then they're causing eclipses. So that's an eclipsing binary star, and they are not rare. In the following decades, then systematic observations of variable stars were taken, and they revealed certain differences in the light curves. For example, then people started to discriminate between a variety of different types of variable stars, like novae, like long period variables, short period variables. And this then fueled some theories regarding the underlying physics of variability. There was one idea by the scientist John Goodrich and by the scientist Edward Pigott that variability might be caused by eclipses of a star by the planetary companion, but they were ruled out. And then another theory was proposed that at least some periodic variability might be caused by pulsations instead. So the observational studies by Harlow Shapley and others around 1915, and then also some theoretical studies by Eddington, established finally the pulsation nature of stars like cluster variables. We nowadays call them our Lyrae stars, Cepheids, and so on. The underlying mechanism of that pulsation What is that? So if you're in a normal AFG star, then helium is neutral in the stellar photosphere. But deeper below the photosphere, at about 25,000 to 30,000 Kelvin, we have the helium-2 layer, first ionization. Second ionization starts at about 35,000 to 50,000 Kelvin. When a star is contracting, the density and temperature of the helium-2 layer is increasing. The helium-2 starts to transform into helium-3, second ionization. And this is then causing the opacity of the star to increase. And finally, the energy flux from the interior is effectively absorbed. This is, of course, causing the temperature of the star to rise. So it's beginning to expand. After expansion, the helium-3 begins to recombine into helium-2 again. So the opacity is dropping. And this is then lowering the surface temperature of the star. Then we see contraction. And after that, basically, the process, the cycle starts from the beginning.
Okay, so it's pretty it's pretty weird to think stars to pulsate. I think when I encountered this concept at first, it was not immediately, let's say, straightforward to grasp. How I would at least not intuitively imagine this to be, yeah, very easy to to imagine as a phenomenon. But you mentioned indeed the type of variable stars of Cepheids and Lyrae. I don't know if my pronunciation of the second time was was correct. I struggle quite a lot. But I would like to ask you, what are the properties of these variable stars, and let's say, why are they used? Which is let's say a recurring concept that I would find. Why are they used as let's say distance measurement?
Yeah, so one of their most distinctive property is that they show a regular periodic change in the brightness. And this is something that is interestingly linked to their distance over multiple steps. So when we think about measuring astronomical distances, I'd like to start with the question, how do we estimate distances in everyday life? So distances to places we just cannot reach. Some passing trains, some passing cars, some passing ship, how we do that. So one idea we have is in everyday life is parallax. Even if somebody is knowing this term, they have for sure recognized the effect. So the apparent angular movement of an object when viewed from different positions. You might have noticed that effect when being a passenger in a car looking out of the side window. You can see objects nearby are passing quickly, whereas objects far away pass more slowly. And then when measuring this angular movement carefully, you can figure out the distance. So there is another idea. How do you estimate the distance to a bright light at night? Suppose you're looking out of your window at night and you want to know whether a distant light is from a street light, car, house, something else, and how far away it is. Then you're relying on very specific properties, such as the color or movement of that light source, to figure out which kind of object you're dealing with. And from that, you know the true brightness. You know, for example, how bright is the light of a fire truck? How bright is the light of an ordinary car? And now from that true brightness and the brightness you're observing, you're seeing, you can now guess the distance, or when measuring the brightness with a photometer, you could even calculate it, the distance. And that's also what astronomers basically rely on, because of course we cannot make use of a measuring tape and go to a distant star, but we have to figure it out otherwise. So first figuring out what is the type of an astronomical object. Then as a second step, knowing the luminosity or the absolute brightness, absolute magnitude of that type of star. Then compare the observed magnitude to that to calculate distance. For this, we have an equation called the distance modulus. That's very simple. You just have two parameters, the observed and then the absolute magnitude. And there's one difficulty, how to get the absolute magnitude. In the example with a fire truck, it's easy. You might have seen it from very nearby, you have seen it from far, you know what's the absolute magnitude. But we just cannot travel to a star and measure it. So we have to make use of something else. In fact, in pulsating stars, the period of pulsation is correlated with the luminosity of a star. And this relation can be calibrated as the period luminosity metallicity relation. So it relies mostly on period and luminosity and also a little bit on metallicity. And this means when knowing the pulsation period, and that's pretty easy to measure, we can calculate the absolute magnitude. That would be just like, for example, bright fire trucks would blink a bit faster. It's very closely related to that example. And the complete recipe to measure the distance to a pulsating variable star is then we measure the apparent mean brightness that we can observe. We measure the period. Then, using the period luminosity relation, we can get the absolute brightness. And we can then solve for the distance by making use of the quite simple equation of the distance modulus.
Okay. Why are they called, why these type of variable stars are called standard candles?
Yeah, they are called standard candles as we can just use them that way. They have a constant mean brightness, and this helps us in carrying out calculations by making use of this distance modulus equation, because it would just not work if their brightness and the period were distributed by random and would not show any connection. So in this way, we can make use of them to create distance maps, to create 3D maps of structures within and beyond the Milky Way. Our Lyrae stars help us with structures in the Milky Way, and Cepheids allow for measuring distances to other galaxies, and are one of the first steps that we can make use of for the cosmological distance ladder. So to measure distances further and further out. Okay, and what is the origin of these candles? Meaning, how does a star? Okay, let's say, why does our sun is not a variable star, and how there are variable stars? How do these phenomena originate? Yeah, so nowadays we believe that being a pulsational variable star is in fact one stage in the evolutionary history of a star. So it should happen to stars, to most of the stars. Okay, but let's say, is it granted that every star will undergo this phase of being a variable star, or do we know of any case where we had seen stars not undergoing this phase? Or seeing it from that direction, it's kind of difficult, because we just cannot look back whether a star has never shown this behavior. We don't know. But what we know nowadays is that it is common for stars of certain masses. And we know we have a few rare encounters where we have seen stars starting to pulsate. So we know a few stars where we have observed the process to set on.
Okay, like how does, let's say, this process kicks in? Meaning, when what happens at the time t when our sun or whatever star in the universe starts pulsating? Why does it start pulsating, whereas it was before not doing so?
The pulsation process, like I have described it before, this is just because the star is not in a hydrostatic equilibrium. So the pressure from inside and the gravitational force are not canceling each other out, but this pulsation process starts to happen. But our Lyrae stars are much smaller than our sun, so about 10% in mass.
Okay, and instead, what do these standard candles, what do these variable stars, let's say, let us make us understand, let us infer about let's say, their surrounding, and about them, let's say, more broadly, the evolution and the properties of the galaxy, or let's say of the local space they are situated?
So they are very good probes of the early galaxy, because in that way, as they are prevalently found in globular clusters, which are very old, and also in dwarf galaxies, which are stretched in the shape of tidal streams around our galaxy. So we can use them to map those features. So we can make use of them to map, for example, Sagittarius stream, which is a tidal stream, which elongates from the core of the former Sagittarius dwarf galaxy. And in that way, we can probe those structures. However, for probing the early universe, pulsating variable stars are not the best choice. For cosmological distances, we need supernovae, and with them we can measure distances out from our local group to just the most distant galaxies.
Okay, can we let's say, can we use these tools? Can we use these stars to, let's say, go back in time and probe the universe, and let's say the dynamics taking place at, let's say, very early times after the Big Bang?
That's actually, it would be cool if it would be possible, but we just don't have those resolutions. When we go back in time, we have to go to more distant objects, to higher redshifts. And if we would want to use those stars, then we had to resolve those galaxies into individual stars and pick out the correct ones. And this is just not possible with nowadays technology, and also not, I think, with what will be available in the near future. So that's why we're making use of supernovae, because they are so bright that we can see them even in very distant galaxies.
Okay, it sounds, let's say, very frequently, even when talking, having a conversation with other guests, sometimes it comes this sort of point which is kind of frustrating, because they'll say the understanding of something, of any matter, is more of an engineering problem than, let's say, a physical problem or mathematical problem, meaning we just don't have the tool, we just don't have the equipment that is, let's say, that is good enough such that to understand those processes. But yeah, I guess it is just, it is, yeah, it is what it is. I have to say, just is. Okay, and instead, I would like to ask you again, now we go back to the machine learning framework, where, let's say, where does machine learning enters the picture here in variable within variable stars? How do we use it? And of course, what benefit? What are the advantages that we can reap from the implementation of machine learning?
Yeah, so what is very important here about machine learning is that it enables us to go quickly and precisely through massive amounts of data. And in that way, we can process data, so especially like curves from nowadays large surveys like SDSS or PennSTARRS or CTF, which is a Zwicky transient facility at Caltech. And in that way, we can filter information, but we can also understand information better. That's especially important when we have data sets that are just not fulfilling the criteria on data quality that we want to see. Because, for example, the survey was designed initially for a different purpose. So PennSTARRS survey, for example, was designed to discover asteroids. But we can also, and I was doing that, use PennSTARRS because of its large coverage of the sky to find variable stars. It's not that easy when having a survey that's designed for something else, but machine learning is extremely helpful to filter out information even from very sparse data set. So the main problem here was that PennSTARRS only takes a few observations per week, per month, and then a lot of those observations from PennSTARRS were also quite noisy. And so I initially had to throw away a lot of information, and I didn't have much information at that time. And so classical methods like for period finding were struggling with that. Whereas with machine learning, I was able to process those data and finally find very precise periods of those stars. So machine learning has absolutely helped with the data processing. And this will also be the case with more recent or upcoming surveys, just like with the LSST survey, which is the legacy survey of space and time, which will be carried out by the Vera Rubin Observatory starting 2024, hopefully. And what will happen there is that we will get petabytes of data, and those data need to be scanned automatically. And we want to scan those data really fast and making use of machine learning. So we, for example, can trigger follow-up observations. This means when something interesting is discovered automatically, then also automatically other telescopes should take over and point to where that source is to take additional data.
Okay. It looks very exciting. Let's say then what you can actually get from all of this at the end of the day, and how actually a big of an advantage, a big of an extension is the work we have been carrying out, let's say, manually so far. But I would like to ask you, you mentioned before about if something does not match your data, and which I think relates to the point I would like to cover now, which is, let's say, astronomical, let's put it this way, astronomical anomalies. What do we mean by anomalies? What is an anomaly? And how do we find it in the sky, when looking at the sky, and in astronomical objects?
Yeah, what I mentioned before is when data or data quality is not matching up the typical data quality we would need to run certain algorithms. That's a problem. But anomalies more points towards something interesting. So anomalies in the sense are rare and interesting objects. We also call them 1 in a million events because they're also rare and we have to find them in a bunch of data. So to just make one example what those rare events are. There was a recent publication by El Bedri et al. And what they found is an extremely low mass white dwarf. So when a star dies, there's a 97% chance it will become a white dwarf. But in very rare instances, a star can become an extremely low mass white dwarf. That's a subcategory. It was predicted by Siri, but there were no observations of this class of binary star until 2021. And using data from Gaia and from the CDF at Caltech, they narrowed down 1 billion stars to about 50 potential candidates, and then they carried out follow-up observation based on that. They first tried exactly that process. They narrowed down the information to find likely candidates, and based on that, taking in more information by follow-up observations, and then refining the process of finding those objects. And finally, they found about 20 of those extremely low mass white dwarfs. And that's exactly this kind of discovery that requires those massive data sets. Think about going down from billions, millions of observations to finally find 1 or 2 or 20 of those objects. And these are discoveries in this range that will be more and more possible with surveys just like LSST, plus the right tools, which are machine learning here. And that's just possible because LSST will deliver a very large on-sky footprint. So it will cover a lot of stars on sky and a high cadence. So it will re-observe the same stars quite frequently. So we then have very highly resolved, temporally highly resolved light curves, which allow for detailed light curve analysis. Plus, we can do statistics from large data sets. Plus, we can filter out rare objects. And that's exactly big data applications like we see them nowadays in astronomy.
Okay, you meant so basically you just clarified how this big data set play a role in machine learning and in the application of machine learning with this task. What is instead the Sloan Digital Sky Survey? Because that's one of the, let's say, the big one of the big names when it comes to astronomy and and data in astronomy. Well, what is it? Why do we have such a survey? And let's say, where does it? Why is it important within the application of machine learning to indeed astronomical studies?
Yeah, so SDSS, the Sloan Digital Sky Survey, is for good reason so famous because it is a major multispectral imaging and spectroscopic survey, and it was the first fully digital sky survey beginning in 2000, making use of a CCD camera. So before, we basically had photographic plates that one needs to develop, that one needs then maybe to digitize, and that's a very, very time-consuming thing. But with SDSS, for the first time, it was possible to take astronomical images more precisely and faster, and in that way we were able to take more images. And this project, which began in 2000, is still ongoing. So we're now having 23, 24 years of SDSS, and we also have specialized sub-surveys like, for example, EBOS and other surveys, and all of that is taken at a dedicated 2.5 meter wide-angle optical telescope at the Apache Point Observatory in New Mexico. And this was basically really our start into digital photometry, digital spectroscopy, and other surveys like pan-stars were drawing from this experience. And also the LSST survey will draw a lot from this experience and even take it further by making use of machine learning, not only for interpreting the photometry taken, but also for deciding where to take photometry, but so really where to point our telescopes.
Which brings me to the to the next question immediately. How do we decide where to point our telescopes? Well, let's say, when do we understand? How do we understand when it is the right moment to do so, and how do we optimize this to decision?
Yeah, you can imagine when having such a big telescope with a lot of possibilities, we want to fully max them out. And what we're doing here is called survey strategy planning. And it's influenced by both our science goals, so what we want to observe, and by the movement of celestial bodies, so stars, planets, the moon, and of course the weather in addition to that. So our science goals, we have very different science goals, and they lead typically to different objectives, like taking images of many objects versus long exposures, so taking exposures of the same object over a long time, versus revisits, so coming back to the same object and observing it again. So those are competing science goals. And then regarding the movement of celestial bodies, including our own planet, you might have seen that with the seasons changing, we see different stars on the night sky. For example, in the northern hemisphere, we see less of the globular clusters in the summer sky, and it's just the opposite for the southern hemisphere. And the reason for that is just the movement of our Earth. So to understand that, remember that the Earth rotates on its axis every day while it's revolving around the sun every year. And so you can only see the constellations when your part of the Earth is facing away from the sun, so when it's night. And combining all of that, as the Earth orbits around the sun, the constellations seem to move slowly to the west over the course of a year, and we see different parts of the sky at night. And so with the telescope, of course, we can also only observe certain parts of the sky at a given time. That's one thing we have to consider when planning observations. Are the objects we want to see visible? Are they visible as far as possible high in the sky? Because we just don't want to look through a thick layer of atmosphere close to the horizon. So higher in the sky is better. That's something we have to consider. And another thing we have, of course, to consider are weather conditions, or whether, but that's predictable, the moon as a very bright object is too close to the object we want to observe. So there are a lot of factors that go into our observing, into deciding on where to point a telescope. Some of them are more general, like our competing science goals, like the seasons, and we can put them into survey strategy planning because they're general, but we also have to keep track of things like weather conditions. And here a machine learning algorithm can be very, very helpful because it can be trained to maximize those objectives. Let's just imagine you have, for example, some objects which you want to be observed, let's say, once or twice a night. It's not so important if they are observed once or twice. And then you have one object that you want to keep track of it for sure, for let's say for 10 days in a row each night. And then you have two competing objectives with two small projects out of a big amount of projects. And this is something that typically was just tried to optimize it by hand, but nowadays machine learning is taking care of that.
Okay. Let's say I would like to talk about now, let's say make a sort of a jump back, because I would like to discuss what are active galactic nuclei. It is this, let's say, funky term to describe what is a galactic nuclei, and what is, let's say, the structure. What is the structure surrounding an active an AGN, and yeah, what are these funky objects?
Yeah, so AGNs are basically galaxies that are not so quiet, and in fact they were first detected as radio sources, but they can nowadays also be detected by their spectra. So an AGN is considered to be a galactic core hosting a massive black hole, like in each galaxy, that is accreting matter and is displaying a strong luminosity from its jet. So the nuclear region of the Milky Way, in contrast, just lacks sufficient luminosity to satisfy that condition. So the Milky Way is not an AGN. AGNs are the most luminous and persistent sources of an electromagnetic radiation in our universe. And this means they can be used to discover distant objects. So this is something when you want to look back in time very much. And astronomers have also classified different types of AGN based on their observational characteristics. The most powerful AGNs, we know them as quasars, which are then followed by, for example, blazars, which are an AGN showing a jet of light and energy that is pointed very much toward the Earth. So those categories are now believed to just depend on the orientation of the AGN with respect to the Earth. So there's a unified model of AGN that is the concept of a large range of observed properties of the AGN can be just explained by a small number of physical parameters and the orientation.
Okay, you mentioned just now about the jet that are emitted. Well, these jets, I've seen not, but I've read they can manage to travel at almost, not in every case, but in some cases they can manage to travel at almost the speed of light. How, first of all, this is possible? Why does this happen? Because it is not a, let's say, quite a simple physical phenomena of these jets traveling at almost speed of light.
Yeah, so relativistic jet is forming when a black hole spins and the accretion disk is strongly magnetized, perhaps on account of gas accreting at high latitude beyond the black hole sphere of influence, and then those magnetic field lines speed up the matter and then it's expelled. And this is exactly what is a relativistic jet.
Okay. How do they interact with the environment?
So what they do is especially that they blow out matter, and in that way they are also believed to be or to have a big influence on star formation rate within a galaxy. Okay.
How do we observe AGN, and let's say what do we observe? Because I mean we have you said they are one of the strongest source of electromagnetic, one of the strongest source of one of the strongest electromagnetic sources. But what do we observe? Because at the center of the galaxy there is black hole. A black hole is black. What do we observe when we see AGN?
Yeah, so the first observations of quasars, of AGNs, were in fact radio observations. So I recognized there is a radio source that's just always there, and found it to be close to the center of our Milky Way. But nowadays, quasars in general are observed by photometric all-sky surveys such as PAN-STARRS, SDSS, and will also be observed by the upcoming LSST. So first, there are just some background sources. That is also found a bit in their name. Quasar means a quasi-stellar source. So quasi-stellar source is a star-like appearing source, but it's not a star. They appear seemingly like point sources in photometric surveys, but we can make them out by their very distinctive variability. However, in addition to photometry, what's also quite important are spectra, and SDSS, for example, took spectra of almost 1 million of quasars.
How does instead, let's say, how does machine learning indeed helps us in cataloging AGN and let's say describing, cataloging their properties, and also what properties do they have?
Yeah, so machine learning can help, for example, to first filter out AGN from our photometric surveys by making use of the photometric variability. And then once they're known, they can be studied further by specialized observing programs, like, for example, with spectroscopy or with X-ray observations, where X-ray observations provide to be one of the most reliable methods to identify AGN, because the X-ray emission from other astrophysical processes is very weak by comparison. So then once we have found them, we can observe them multiple times, continuously, whatever we want to do with them. And we can, for example, keep track of when they show which level of activity. So we know some galaxies that have become quiet in a meanwhile and then started accreting again. So it's not a process that's either there or is not there, but accretion can set on and can stop after a while when just the matter is exhausted that can be accreted, and when some gas clouds come close, then it can start again. So that's really a process that is changing over time.
Okay, and let's say what is the role active galactic nuclei play in galactic evolution?
So the active galactic nuclei, what they are doing is, it's now believed that most, if not all, galaxies contain a supermassive black hole, and that they play a very crucial role in the galaxy evolution. When matter is accreted, a supermassive black hole is releasing energy, as we've seen, which may have an effect on starting or stopping, so modulating star formation, and also constraining the growth of galaxies. And it's believed that AGNs can be divided into two broader fundamental categories, each with its own feedback mechanism. One is the radiative mode of feedback that is occurring in gas-rich galaxies, when substantial star formation is occurring and the young AGN are growing rapidly through efficient accretion of cold gas. A fraction of the energy released by an AGN is then transferred into the surrounding gas. It's creating a thermal energy-driven wind and gas and dust might be expelled from the galaxy actually. So this can stop star formation, but can in fact also cut off the fuel supply to the AGN itself, and then star formation can set on again. So there's a lot of dynamic taking place regarding what an AGN actually does to a galaxy.
Okay. And I would like to ask you, let's say, starting to wrap up a little bit, how do variable stars help us to infer the geometry of space-time?
So the geometry of space-time, it's typically referring to the curvature, and it's measured typically by its lensing effect on spots in the microwave background. So that's something that's very far in the literal and any more arithmetic sense from what are variable stars. If the universe has a large curvature, it is massive enough to recollapse, ending the universe in a big crunch. We believe this nowadays, and we know we now see how the microwave background should look like under this and that condition. But variable stars, supernovae, Cepheids help us to infer something else, and that's the expansion of the universe. And we can do this by building a distance ladder. So this is something that starts with very nearby stars where we can make parallax measurements. But then we are soon going out to step 2, standard candles, which are Lyrae stars and Cepheids, and in a third step also include type 1a supernovae, so at greater distances where we cannot observe individual stars and Cepheids are no longer useful. Supernovae are still bright enough to be observed, and they're like carefully being traced. Then, when this is no longer possible, we have our fourth step, and this is measuring the redshift. So why we call this a distance ladder is that we can verify the correctness of each of those methods by making use of some objects in a distance where 2 or more methods are possible to be applied. And then we can, calculate the distance by, let's say, for example, parallax and by pulsation. And then we can compare them. Then we know how we have to, or which parameters we need for our causation based calculations, and then we can use that how far ever we can go with it, and then take over with supernovae, and then take over with the redshift. And so we can, for example, understand in detail the expansion of our universe, and with that also something about its origin of the first structures. Okay, and so to close our conversation, I would like to ask you, I don't know if you have heard of one of the, let's say, recent discoveries, let's say relatively recent discoveries made by the James Webb Space Telescope, and it appears that the James Webb Telescope found a galaxy which it is too big for the age it has. And yeah, so basically it is this, I am looking at the article at the moment because I saw some videos about it, and basically it implied the fact that this galaxy is too big to exist at the time it existed. In a time where it was very early in the history of the universe. And I would like to ask you, as we can see, the James Webb Telescope is already, let's say, giving us some, let's say, hard, let's say, it is giving us a lot of
thoughts from our mind, and yeah, a lot of new discoveries that we will have to deal with. What do you think? What do you believe? Maybe the sort of the ceiling of the James Webb Telescope, meaning how far, how deep, and how precise can we probe the universe in a way which is fundamentally different than what we did with Hubble, and that in general we have been doing so far.
Awesome. I'm not an expert on that, I have to say, because for my kind of research, I'm not making use of any JWST data. I would also have to look a bit more into that, and I have seen the discovery of that galaxy, and I think it's a really exciting thing. What I think is very important nowadays is that we know in a not only in a literal way in which direction to look, so for what to look. And I think in that way, the James Webb Telescope, together with applications like machine learning and combining that with simulations, is a good way, because those data taken with JWST, we can also compare it to simulations. We can compare it to simulations of the earliest stages of galaxy formation, and we can see if there are any discrepancies. Like with that galaxy, we can in that way also rule out certain models. And in that way, I think it's an extremely valuable instrument that we have nowadays.
Okay, hopefully you may come back one day and talk to us about the latest discoveries of the James Webb Telescope. But
yeah, that would also be great, but I'm not sure, but maybe as I'm working also generally in the field of machine learning algorithms, it could be that I develop some kind of algorithm that's also applicable to those kind of data. It's totally possible.
Okay, great. Then we hope for the best. And Nina, I want to thank you very much for this conversation. It was full of stuff. I was writing down the points that we were touching upon, and yeah, it turned out we talked about quite some stuff. So it was extremely exciting and interesting. Thank you very much for your time. And yeah, I hope I will may have the chance in future to get to talk to you again about some new maybe discovery that indeed we will be able to carry out. But yeah, that was it. We can wrap it up here. And so thanks everyone also for following along with us. This was Math and Beyond the podcast. And I will see you in the next episode. Ciao.
Thank you.